That was easy.
Hi, so I wanted to assess the validity of everything in this Tom Scott video about sorting algorithms and big O notation. So let's get started. I'm not going to be able to show you the video because of copyright ID reasons, but you'll see all of my live reactions to things, and I'll give you some information about what he's actually saying and whether it's true or not, and then give a grade at the end. So let's go ahead and get started. Okay, so it appears that Tom Scott's problem during his internship was he's got a whole bunch of different photos and they are just not categorized whatsoever. They just have a random name to them, and let's see what he does with it. So apparently this job was not very interesting to Tom, so what he decided to do was he wanted to make this more interesting, try to automate it, try to be able to search things really easily instead of just having to look things up manually. So that's a very good thing that I would motivate a lot of people to do, is to, if you see a problem that you are doing over and over and over, write a program to automatically do it yourself. If you have something that you are doing, let's say 2 or 3 times at least, then just automate the whole thing. If you're already a programmer, my advice is if you're writing the same piece of code multiple times, just extract it out into a function and then just call the function over and over. So that's a really good advice by Tom here. So his initial solution was, if you have a search query at the top, you will just go through all of the descriptions of the things, of the photos in this case, and just return the ones that happen to match and put those at the top. So essentially it's doing a 0-1 sort right here. So I think what he's going to get into is, in general, sorting algorithms where you have a bunch of data and you want to sort them by some particular field. So in this case, it's 0 if the search does not match the particular photo, and 1 if it does match the particular photo. So apparently his code was really slow when he started to work on bigger and bigger data sets, which is definitely an approach that he didn't actually say explicitly, but is what he actually did. Was, if you have some algorithm and you want to evaluate its performance, start on a small data set and work your way up, and then see how the performance degrades over time. So how much slower does it get over time? Does it only grow logarithmically in the size of the data set, or is it linear, or is it like exponential, or what is going to happen? And so he probably implemented a sort that is not very good, and that's the reason why his code was pretty slow. So let's see. So he's saying here that there are lots of different ways to solve problems, and a lot of them take different amounts of time or memory to execute. And that's certainly true. As someone who's taught many times intro programming, that is definitely the case. So there are lots of different ways to approach problems. You can store data in some other ways and loop through it in other ways, and there are whole different effects about sometimes the cache in the computer is really, really useful in how you traverse data, versus if you traverse it a different way, it slows your code completely. So let's see. All right, so he's going to talk about bubble sort here, and this is the prototypical initial sorting algorithm that I usually teach when I teach this kind of thing. And bubble sort is a really good introductory sort because it allows you to get incrementally closer to a solution over time versus just waving it out of thin air. But the problem with it is that it's really, really slow in practice. So let's see where he goes with this. So for those who don't know what bubble sort means, it's you look at each individual pair of consecutive elements in this collection. So these blocks, I guess, as they call them. And if they're in the right order, leave them. If they're in the wrong order, swap them. And you just continue until the entire collection is sorted. You'll never put 2 elements in the wrong order, because if they're in the wrong order, you put them in the right order. And if they were in the right order before, you never put them in the wrong order. So you will always get incrementally closer, but let's see where he goes. Okay, so he said that you look at each individual pair of consecutive elements in that particular order. You don't actually have to do that, but that's actually the most efficient way of doing it, and for a whole bunch of different reasons. So just to note that there are many other ways to actually approach this, such as if there's any pair of unsorted elements, then swap them. It's not necessarily you have to go through the entire collection in order to find something to swap. So his approach, which is the classical one, is the fastest one of this type. It's just that it's not the only one. Yeah, so he just said that bubble sort is terrible, and I actually agree with that. So it's not as bad as other terrible sorting algorithms, but they are terrible on purpose for a lot of different reasons. So bubble sort is actually, he's probably going to show that it is n squared running time, because if you take a reverse sorted list where the biggest guy is at the front and the smallest guy is at the end, then it takes n steps to move the biggest guy from the beginning to the end. At that point, you have one element at the end, which is in the right place, but the other n minus one are still reverse sorted down here. And then you can only move one element in the next pass, according to this algorithm. So you can only fix one element every single time. And that's going to take n squared time, because you got n things to place, and each one takes n time. And it turns out that you generally can't get better performance than that, even in the average case, because of how bubble sort is usually implemented. So let's see where it goes. I really like the little animation here of showing that it's an actual square. So you use like squares of squares to actually depict the actual running time. I really like that here. So one thing that is not technically right is that he said that it has a big O of n squared. But what is the n squared thing? So n squared is the running time here. And to be totally precise here, the big O says that the running time here is going to be some number times n squared operations in total, in the worst case. So among all possible inputs of size n, every single one of them, no matter what you feed into this algorithm, is going to take at most some number, let's call it c, times n squared. So maybe it might be 2n squared, or however we're going to count the operations. It's going to be some fixed number times n squared at most. But it could, for some inputs, it might actually perform really fast. So suppose that we have a completely sorted list right now. So then the bubble sort algorithm only takes one iteration, one pass through the array. And so therefore that runs in big O of n time. And if you have a constant number of swaps in total that you need to perform to get it sorted, it will still take big O of n time. So on some inputs, bubble sort is really, really good. And on most of them, it's really, really terrible. We measure big O in terms of the worst case runtime. And there are some reasons to consider the best or the average case, but usually we consider worst case because we want to give some guarantees about the algorithm. So that's what big O means. There are different types of things like big O, which talk about it runs in at least this much time, or it runs in exactly this time, because big O says it's this number, this amount, or less. But it could be a lot less. I like the different pronunciation of Donald Knuth. He said Donald Knuth, and that's totally fine. There's a video that's going to be coming out of my channel which has like 15 letters in the person's last name, and there are many different ways of pronouncing that. That's just how the field is. I like how he says that it's the big O notation is about the big picture sense, because it's swallowing up any smaller factors that may be at play. If the input size is really, really large enough, as long as it's sufficiently big, then these, the lower order terms, as we call them, are going to fade away into obscurity in some sense. If we have a really, really tiny input, then other effects start kicking in, like maybe how fast the cache is on that particular run. If we have a moderate size input, then the n squared effects might start peeking in, maybe. It just really depends on how this thing is implemented and how the constants in front of the n squared, or whatever the runtime is, and the lower order terms and how they relate to each other. And it actually depends on the input itself, because remember, big O is worst case. It's at most that number. And so the actual performance might be way less, and it might depend on other factors too. This is just a guarantee if the input is sufficiently big, how slow the algorithm is at worst. I'm not so sure about that. So he said that the lowest complexity that an algorithm can have is big O of 1. Yeah, in an algorithmic sense, yes, but it's not the lowest big O that is possible. So there are some things in my own research where you have big O of something that is strictly less than 1. So like 1 over n, for example. It's not something that is really algorithmically realizable, because anytime you do one step, that's already a constant amount of work. So anything that's non-trivial is going to be a constant amount, but sometimes the big O can be as low as you want. So it doesn't have to stop at a constant number. It can go as low as possible. That was a perfect description of linear time. It proceeds at a steady rate. If you double the number of inputs, the processing time doubles. I completely agree. All right, so he's going to talk about insertion sort, which is another common, bad in some sense, sorting algorithm. That's an alternative to bubble sort. Yeah, so he just described what insertion sort is. No issue with that. Good, perfect. Because he said that two algorithms, if they have the same big O runtime, which insertion sort and bubble sort do here, that does not mean that they perform the same amount of work. They don't take the same amount of time. Mainly because the lower order terms can take over, and the constants in front of the n squared can be different. So like bubble sort could be like 8, and insertion sort could be 4. And even though they have the same big O, which means in general their graphs of runtime are they look the same from a distance. If you squint really far away, they look the same, but the actual performance may not be exactly the same. It's just, on the whole, the relative difference between them never changes. So the one of them is gonna be, let's say that they run in exactly n squared time, just for simplicity. Then that means that the ratio of their runtimes never goes above a certain number. So like one is at most twice as fast as the other one. It's not like going like this, where one is just shooting to the moon like GameStop, and the other one is just hanging around. I'm only taking a certain amount of runtime. So that's why it's important to distinguish n squared, big O, versus the actual performance of the thing. Okay, so he's describing quicksort, where we've done this on the channel, where you pick a pivot element, put all the smaller things on one side, all the bigger things on the other one, and sort the two halves. Because you know the pivot must be at the right place, because all the smaller things are on one side and all the bigger things are on the other one. Good, good. He actually said it correctly. Thank goodness. Because so many people get this wrong. I think there are even some professors who get this wrong. So he said that the worst case is still n squared. And the reason for quicksort's bad performance is if we pick the either the biggest or the smallest pivot, depending on how we're going to count it, every single time, then we're only fixing one element, and all the other ones are just in the same order. They're not modified. And so we're going to get essentially the same performance as bubble sort in that case. And he mentioned here why it says n log n here. He said that on average, the quicksort algorithm takes that much runtime, n log n. And there are a whole bunch of reasons why that's the case. So if you if you analyze a randomized version of quicksort, where you just pick a random element in the list, then on average, the performance is n log n, because on average you're going to pick the middle element of the list, and that's going to roughly sort the two halves are going to be of equal size in expectation. Another reason why it is, and we've done this video on the channel too, which is trying to find the median of a list in linear time. So in order to find the middle element to have the two halves be of equal size, we typically want to find something that's close in the middle of the list. So therefore, finding the median is the theoretically optimal choice for that, because it's dead in the middle. So you can actually find the median in a list in linear time without having to sort it first, which is pretty dang cool. The problem here is that the constant may be way worse than n squared. So technically the n log n one is going to win out for large enough n, but for small enough inputs, the n squared one might be the better one on average. Or it might be worse. We don't necessarily know. It doesn't consider the actual performance. It's really about if the inputs are sufficiently large enough, which handles infinitely many different sizes of lists and only a finite number for which the answer might be different. He's not going to go into the mathematics, and I don't blame him because of how popular his channel is, and he doesn't want to alienate his viewers necessarily. But log n is exponentially smaller than n, and so it is definitely a lot better. It's actually shown that comparison-based sorting can't possibly be better than n log n. So n log n is the limit to how good you can do in a comparison-based sorting algorithm, which is like quicksort, bubble sort, whatever. So in some sense, quicksort is the fastest sorting algorithm that does comparisons, which is pretty dang cool. Oh God. Oh God, bogosort. All right, let's see where he goes with this. Yeah, so bogosort, he just explained, is randomize the list, check if it's sorted. If it's not, go again and try again. And the thing is that technically this isn't really an algorithm because it might not actually stop. Because we just might produce a list that is not sorted over and over and over and run for infinite time, which is not what an algorithm is. But let's see where it goes with this. Yeah, so it went away from the screen, but he said it was big O of n plus 1 factorial. He actually was very precise on that, which I'm actually very, very surprised he did that. That's very, very good. So factorial is way worse than n squared. Forget n squared. N squared is efficient compared to bogosort here. There's actually one algorithm sorting algorithm that I really, really like called quantum bogosort. He may even say it, which is the idea that you have a different permutation of the list elements in a different universe. Stay with me. And if the list isn't sorted in that universe, destroy the universe. And so the universe that has the sorted list in it, that's the one you keep, and you can extract the list from that. And the big O of that is it really depends on your model of computation. But anyway, there are a lot of esoteric sorting algorithms out there, and I love all of them. There's another one which is divine sort, which is the fastest sorting algorithm out there possible. Although it doesn't really sort, but we'll see. Divine sort just says the list that we get, we will assume that it has been given to us by some higher authority, and so therefore we are not smart enough to understand why the elements are in that particular order, so we might as well assume that it's sorted and just return the list. So basically, if you get a list, return the list, don't modify it. So it runs in big O of 1 time, constant time. So it's the fastest sorting algorithm out there, but it's a different definition of sorting, I guess. But anyway, let's get back into this. All right, that figure I think is from some website. Has he actually cited that? I'm not sure that he actually cited that. So that figure we actually used in a course where I'm teaching right now, and it's he didn't actually cite it, so that's not good. But I like the figure really much because it tells you, it gives you a visual representation of how slow some of these algorithms are. Note, so one thing that you should note is that these aren't the actual performance. This is just an illustrative example. It's not that they actually are this much better than the other algorithms or worse. It's just a visual representation. That's all it is. I like that he says that it's just it's an approximation to figure out which algorithm to use. The real test of whether to use one or another is to actually run it on a real computer and profile it. That's something I tell even my theory students. I tell, if you want to check whether one algorithm is better than the other one, in practice, actually profile it on a real computer, because there's just no better way to actually test the performance of them. Okay, so he wrapped up right there. So he said like the better solution was to use something that is different than sorting. So instead of having this search query with the photos in it, you just put them into a Word doc, for example, and you are able to search it there. So I like that a lot more, because the client required the ability to just find things. And remember that the sorting that he did was a 1 if the item matched and a 0 if they didn't, and it populated the results at the top. So effectively, there were only 2 values that they needed to work with. And so maybe there's a better algorithm for that. So for example, radix sort exclusively works on integers, and it runs in some sense, linear time. And that is sufficiently faster than n log n or even n squared. But because of the example that he did, he would be able to use that, but he just wasn't aware of that at the time. So that's totally reasonable. All right, so it looks like he's done here. So this is actually a very, very good introduction to Big O. He had all of the necessary caveats. I wish that he went into the mathematics a little bit more. Maybe said that it only works for sufficiently large inputs. He did say something along those lines, but I wish that he included a little graphic where, like after this dotted line, the algorithms make up their minds, and one of them is bigger than the other. Like they can cross a whole bunch of times before then in terms of their running time, but after a certain point, then they make up their minds, and one is always bigger than the other one. Something along those lines I wish that he would have had. So if I had to give a grade, I would have given either an A- or a B+ to this. It's very, very good. It's just that there are some things that I wish he would have done in addition to this. Cool. So this was a interesting viewpoint on Big O notation. If you have any questions about Big O or any of the videos on my channel, please put them into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.
That was easy. That was easy. That was easy.